Hey everyone, and welcome. Have you ever wondered what's really going on behind the scenes of your favorite apps and websites? Well, you are in exactly the right place. Today, we're going to pull back the curtain on system design and break down the absolute core concepts that turn a simple idea into a massive global system. Let's get right into it.
Seriously, think about it for a second. You type a website into your browser, you hit enter, and boom, the page just appears. It feels like magic, right? But it's not. It's an incredibly fast, perfectly coordinated dance of technology. And in this explainer, we're going to follow every single step of that dance.
And look, if you're in tech, doesn't matter if you're a junior dev or a senior architect, getting a grip on these concepts is how you level up your career. These aren't just, abstract theories. They are the fundamental building blocks that engineers use every single day to build our digital world.
All right, so our journey starts with you. It starts with your very first action, the request. Let's trace the path from the moment you click that button all the way to the server that's holding the info you want.
At the very heart of pretty much every web application is this simple but really powerful idea. Your device, that's the client, sends out a request for some data. Then a powerful computer somewhere out there, the server, gets that request, figures out what you need, and sends a response back. It's just this constant conversation happening over and over again.
Okay, but that brings up a huge question, right? The internet is this unbelievably massive network with billions of devices. How in the world does your browser know which exact computer to talk to out of all of them?
Well, the answer is something called the Domain Name System, or DNS. And honestly, the best way to think about it is as the phone book for the entire internet. We, as humans, remember names, right? Like example.com. Computers, on the other hand, they think in numbers, IP addresses. DNS is just the service that looks up the name you typed and finds the correct phone number for your browser to call.
Now, that call doesn't always go straight through. Sometimes it goes through a middleman. A regular proxy server, for example, works for you, the client, and it often helps hide your identity. But a reverse proxy, that works for the server. Think of it like a bouncer or a traffic cop for the server, taking all the incoming requests and deciding which of its many backend servers should actually handle it.
So, the connection's been made. The client found the right server. Now what? How do they actually speak the same language to get anything done? They do it through something called an API. Just think of an API like a menu at a restaurant. It tells the client exactly what it's allowed to order from the server and what it's going to get back in return. It's basically a very clear, structured contract that makes sure both sides understand each other perfectly.
And there are different styles for that menu. REST is the most common one. It's super simple, it's reliable. But with REST, it's kind of like you order a burger, but you get the whole combo meal, even if you didn't want the fries or the drink. GraphQL, on the other hand, lets you be super specific. You ask for exactly the data you need and nothing more. So it's a trade-off, really. REST simplicity versus GraphQL's efficiency.
Okay, so a single client talking to a single server. That's easy enough. But what happens when a million clients all show up at the exact same time? That's when we have to start thinking about designing a system that can handle some serious scale.
You've basically got two options here. You can make your one server way bigger and stronger, that's called vertical scaling, or you can just add more servers to the team. That's horizontal scaling. Now, scaling up is a quick fix, but you're going to hit a hard limit pretty fast. Scaling out by adding more machines, that's how modern systems are built to be resilient and handle internet-level traffic.
But hey, if you've got a whole team of servers, you need a manager, right? That's exactly what a load balancer is. It sits out in front of all your servers and intelligently spreads out all the incoming requests. It makes sure the entire team of machines is working together and that no single one gets overwhelmed.
So, handling all that traffic is one heck of a challenge, but managing the absolutely enormous amount of data that all that traffic generates, well, that's the next frontier. Let's look at how systems store, find, and manage data at a massive scale. The first big choice you have to make is your database type. SQL databases are kind of like highly organized spreadsheets. They demand structure, and they're perfect for things like financial transactions where consistency is everything. NoSQL databases, on the other hand, are more like a collection of different documents. They're flexible, super fast, and built for the kind of massive, messy data you'd see on a social media feed.
Trying to search through billions of records one by one would be ridiculously slow. It would take forever. That's why we have indexing. It works just like the index at the back of a book. It lets the database jump straight to the data it needs instead of reading every single page. It makes finding things almost instant.
Now, to handle even more requests, especially for reading data,
we use something called replication. You have one main or primary database that handles all the new information coming in. Then you create several copies, called read replicas, whose only job is to show that information to users. This spreads out the work and, just as importantly, means if one database fails, a copy is ready to take its place.
But what if your data is just too massive? So big it won't even fit on one machine, no matter how powerful. Well, the solution is sharding. You literally chop up your giant database into smaller, more manageable pieces, we call them shards, and you spread them across a bunch of different servers. This is huge because it lets you scale both your reads and your writes almost infinitely.
And finally, the absolute fastest way to get data is to not go to the database at all. That's what caching is for. We store the most frequently used data in super fast memory. The strategy is simple. Always check the cache first. If the data is there, we call that a cache hit, you get it back instantly. If it's not, that's a cache miss. Okay, fine, we'll go get it from the database, but we'll also stick a copy in the cache to make sure it's faster for the next person.
All right, so we've got all these individual building blocks. Now let's put them all together and look at the high-level blueprints that modern, reliable apps are actually built on.
So traditionally, applications were built as one single giant unit, a monolith. It's simple to get started, but as they grow, they become this tangled, complicated mess that's really hard to manage. The modern way to do it is with microservices. You break the application down into a collection of small, independent services that all talk to each other. This makes it so much easier to scale and update one part of the app without breaking the whole thing.
But how do all of those little microservices talk to each other reliably? Well, a lot of the time, they use a message queue. Instead of calling each other directly, one service, the producer, just leaves a message in a central queue. Then another service, the consumer, comes along and picks up that message whenever it's ready to process it. This separates the services from each other and makes the whole system way more resilient.
Now, in these big, complex systems, network glitches happen. A request might get sent twice by accident. To prevent a total disaster like charging someone's credit card twice, we need something called idempotency. It's this really powerful guarantee that doing an action multiple times has the exact same result as doing it just once. It's absolutely critical for reliability.
So from load balancing and caching all the way to microservices and message queues, every single major app you use every day is built on a combination of these very concepts. The next time you open up Instagram or YouTube, just take a second to think about the incredible architecture humming away behind the scenes. Which of these building blocks do you think it relies on the most?